Then the floor is yours.
Okay, thank you, Tom. Thank you, Tobias. Good afternoon, everybody. My name is Jayahar Sivasubramanian, and this is a presentation on work done by undergraduate students under me. And we are enthusiastic users of SU2. We have been using SU2 for the last 1 year, and this presentation is about some of the simulations done by the undergraduate students who are working under me. So I'm a faculty member at the Department of Aerospace Engineering at MS Ramaiah University of Applied Sciences at Bangalore in India. So the objective, as I mentioned, is to employ the SU2 solver to simulate high-speed flow problems and to validate our CFD results using published results. And for this, we picked two different geometries. One is the Orion CEV, the Orion Crew Entry Vehicles, Exploration Vehicle, and the HEATFLUX. So we wanted to compare also results for equilibrium and non-equilibrium flows for these two geometries, and to also study some the flow features for the HEATFLUX for different scalloping degrees of scalloping. Okay. So the tools that we have used is mostly the SU2 solver, and for grid generation we have used the GMesh solver, which is also another open source software. And so we have used both the open source softwares for this work. The two geometries we have picked are Orion CEV, Crew Exploration Vehicle, and the HEATFLUX. HEATFLUX stands for Hypersonic Inflatable Aerodynamic Decelerator, and it is a geometry which is applicable for atmospheres with low densities. For example, Mars. For if you are going to deploy heavy payloads to any planet with a lower density atmosphere, you need a geometry which would produce drag. And this is one way of producing additional drag by deflating the aeroshells, basically, which deflates as it enters the atmosphere. And yeah, for the Orion Crew Exploration Vehicle, these are some flow parameters that we have used. We have considered mostly angle of attack of 0 degrees because we mostly did 2D simulations, as the computational resources available were only workstations. So we picked 0 degrees and angle of attack and 2D simulations. The Reynolds numbers were 10 to the power of 8 and 10 to the power of 4. For two different Mach numbers, 7.8 and 26.7. These two Mach numbers represents the 7.8 represents a vehicle which is at a lower altitude in the atmosphere, and 26.7 is higher up in the atmosphere. So two different scenarios we have picked for this study. So the grids, we spent quite a lot of time understanding the grids and how the grids affected the solution, basically by doing structured gauge, structured mesh, unstructured mesh, and also fine inflation layer grids. So this the number of grid points varied from almost from 224,000 to 619,000, and as you can see, the grids are well resolved. For example, the inflation layer around the body, we had to have a high resolution close to the surface to capture the heat transfer. So this is another snapshot of the grid that we have prepared for the Orion CEV. So the whole domain, and then the refinement zone, where you can see that the region close to the surface, for example, the stagnation point, also the location through which the shock goes through, has been well resolved using a refinement zone and also an inflation layer. So another snap, a close-up view of the inflation layer is on the right. So we had to do this to capture the heat flux properly. So for example, the pressure data that we picked, we compared it for all three types of grids I have shown before: the unstructured grid, the inflation layer, and structured. And also have compared the theoretical value from isotropic flow equations. So you can see the values compare pretty good, and the grid does not affect the pressure value that much. But when it comes to the heat transfer, it was a totally different story. So for example, for the best solution we got was for the inflation layer, where we could capture the maximum, the peak value of heat flux at the stagnation point pretty well. And there is some difference in the heat transfer away from the stagnation point, but this is our first best solution. So this needs further grid refinement. For example, increasing the number of grid points to see if the grid number of grid points has any effect on the solution. That is something we will be doing in the future. But otherwise, there is a pretty good agreement between the simulation result we obtained and from the simulation result from the literature here. So coming up to comparing the contours from RANS and NEMO. So as I told you in the beginning, we wanted to compare equilibrium and non-equilibrium. For the non-equilibrium, we used SU2 NEMO solver, and you can see there are qualitative differences. The wake is different, and the shock seems to be much sharper in the RANS, but not in the NEMO. But the difficulty we faced was that with the workstation, only a workstation, we could not get the NEMO converged to get quantitative results from a NEMO solver. So all we got was qualitative contour plots from NEMO. Because the CFL number was highly limited, we were using a CFL number of 0.1, and it also needed a long time to converge the solution. So we could not really get a converged solution to get a qualitative results. Only, quantitative plots from the NEMO solver. So the second geometry is a hypersonic inflatable aerodynamic decelerator. Like I said, the purpose of it is to produce drag and slow down the vehicle as it enters the atmosphere. For example, more particularly atmospheres where the density is much lower. A good example will be a Martian atmosphere. So there are several different degrees of scalloping. Degrees of scalloping means depending on the intensity of the pressure load, the scalloping will increase. So that's what it's. Scalloping 0 means almost a smooth surface. Scallop 5 means some deflection is there. Some as the pressure load increases, the imprint of on the scallop, the degree of scalloping also increases based on the pressure load. So you can see that in the figure here. So the condition that we picked is Raoult's number of 10 to the power of 8, which is similar to the second case in the case of Orion CEV. Mach number 26.7, free stream pressure of 100 pascals, and the Knudsen number was decided to be 0.03 based on the altitude we picked, and the turbulence model we used was Palat-Almaraz. So here too, as expected, we had to spend a lot of time focusing the grid refinement around the geometry, and you can see that the close to the body, we are again used the inflation layer to get the good accuracy for the heat transfer values. So you can also see the scalloping details of the scalloping in the high at 20 here in the bottom right. So these are snapshots of results for the different cases. High at 0 means almost smooth surface. High at 5 is some scalloping. There is a high at 10 means even more pronounced scalloping. High at 20 is the worst case where you have a lot of scalloping. I mean, scalloping is not good when it comes to heat transfer. It will definitely increase the amount of heat transfer because it produces local regions of high velocity and low velocity because it forms peaks and valleys, and that will increase the heat load, and that is not something very good. But on the other hand, the advantage is the drag, but the disadvantage is the amount of heat it produces. But still, we haven't studied this for Martian atmosphere. We have to study for the Martian atmosphere to find out how exactly it behaves in the Martian atmosphere. The conditions are similar to its atmosphere. That's what we have used right now. Because the results we had are all for Earth atmospheric conditions. So here again, the bottom, the green line represents the geometry, and the orange line represents the enthalpy distribution. This is for the first one is the scallop 0, which is a smooth surface. The scallop 5 It has a lot of wiggles because there is a scalloping in the surface. So you have these local regions of accelerated flow and decelerated flows. So that produces the wiggle in the enthalpy ratio. So again, for high scalloping 20, you see more of those oscillations because of the change in the velocity and temperature. And also overall, the value of enthalpy has increased. So we used enthalpy to study the amount of heat being generated on the surface. So these are all qualitative results. Again, because this geometry is for, we had results for non-equilibrium. We also wanted to see if we could get the NEMO results. Again, the same thing, we ran into the same problem of not getting the NEMO to converge on a desktop machine. So we are at the point of deciding whether it is even possible to get NEMO results on a desktop computer for grids this size, where the maximum we have is about 620,000. So this is something we are still finding out. We are in the process of getting a HPC system. So when we have the HPC system, it should be possible for us to run longer and get the NEMO converged. And so far, we have been successful in getting equilibrium results. We have even compared, for example, the Orion CEV. We have compared the results with the literature, and it's pretty good. But when it comes to non-equilibrium using SU2 NEMO, we are getting into difficulties with respect to the simulation getting converged. So again, qualitative comparison between RANS and NEMO, also the peak temperatures in the RANS and NEMO, just show that how RANS over predicts the temperature. And with the NEMO, which includes more of the physics relevant for high temperature flows, the temperature seems to be lower, and most likely it is closer to the real values. But we are yet to get to that point where we could compare the results with the non-equilibrium results, published non-equilibrium results. So summary, as I said, these are work done by undergraduate students under me, and they have computed, in fact, even a few more geometries, but I only picked these two geometries for today's presentation. So the Orion CEV and the higher geometries. And with non-equilibrium, we are facing some issues because we have limited resources with respect to computation. But otherwise, the equilibrium results are kind of comparing pretty well with the published results. And so moving forward, we are going to look into how effectively we could use our workstations to get NEMO results. And we are also working hard to get a HPC system at our university as soon as possible. So I want to thank you all for your time, and I will take any comments or questions from you. Thank you very much.
Thank you.
Thank you.
The floor is open for questions. Before, if you can go back to slide 20, because I got the impression when, no, then 19, sorry.
The number is not there, so.
The comparison, yeah, because here in the discussion, I had the impression that you were not happy with the temperature, but it's, I mean, it's okay that the temperature is lower if you have a non-equilibrium flow.
Oh yeah, I didn't mean to say that I'm not happy. I'm saying.
Okay.
I didn't mean to say
quite a very nice computation. And what's the reference value that one should expect for this case?
For the reference value, I don't remember right now. We have to look into the references. But this NEMO solver is very close to the value that's what I meant to say. Yeah.
Okay, thank you. Sure. Are there any comment or questions from the audience? Yeah. Fossati. Can you go back to the slides showing the conditions for your simulation?
Flow conditions, you mean?
The boundary conditions. The initial condition for
Initial flow conditions.
this one? For the Orion C.
What is the question? I didn't get the question, sorry.
Yes, if you can go back to the slides showing the initial condition for Orion C.
Oh, okay, okay.
Yes. Yeah.
Yeah.
Okay, because one element that I was trying to understand is it seems that the density is low, 10 to the minus 7 kilograms over the tree, which means that you probably are in a situation where the is not entirely continuous. So that would be an element to be how have you this point?
Yeah. So Professor Fossati is asking if you took into account the fact that the Knudsen number seems to point to a non-continuum, so the density is very low, and if you took that into account somehow or not.
I'm not sure. I didn't get the question correctly. I mean,
The density in is very low. So
oh,
possibly
yeah.
the continuum hypothesis is broken, and
Yeah, that is a very valid question, and at this density, the continuum is not in fact valid. But that's why we didn't. The comparison for experiments we did only for 7.8. For this, you need a non-equilibrium, the equilibrium results where you have the continuum is also one issue. That's why we didn't compare this result with anything. The comparison is done for 7.8. So it's a valid question. So there is the Knudsen number issue is there. The continuum, the validity of continuum is also an issue there. Yeah.
Yeah. So I don't think one can use NEMO or SU2 say at all in this condition. Yes. Okay. Thank you. Any other question? Yes, there is one more question.
Hello. So you were only dimensional. You were straight. But the mesh you show the entire body you consider its the alpha on the streamline
That's the trick question, but it's I think it's an interesting one. So why you decided not to exploit the symmetry of the problem to reduce the computational burden? Is there something that is not working if you consider symmetry condition, or just more general?
Oh, yeah. I mean, there was some issue. There was some issue with symmetry condition, and that's why we did 2D simulation. But we saw that. I mean, we have raised the issue even in the forum once. When the symmetry condition is used, there was some issue with writing out data also. So students were complaining. So we switched from symmetric simulation, axisymmetric simulation to two-dimensional simulations. So yeah, that was rightly pointed out that we faced some issue with the symmetry condition, and it seemed that the latest version of SU2 the issue has been fixed, because the simulation right now, the simulations run by the students with the latest version seem to not have issue with writing out data and so on.
Okay, and this is both for SU2 and SU2 NEMO, or just for one of the two solvers?
I think it was both. We had issues, symmetry boundary condition, axisymmetry boundary condition. Symmetry was Yeah.
Tend to agree.
Yeah.
Okay. Any other question? Then let's thank Jay again. Thank you for your contribution.